Predict the products formed by the reaction of cis-1-bromo-2-methyl cyclohexane with sodium methoxide. Okay, so let's look at this problem. And so predict the products, products. So we don't know whether it's going to be one or two. We're going to have to find out after we write the mechanism. And then we're looking at cis-1-bromo-2-methyl cyclohexane. That's our substrate, of course. And the substrate here, looking at the name, it tells us that we have a stereochemistry to think about. And then lastly, here we have sodium methoxide. Sodium methoxide tells me that I have something that looks like this. Methoxide, so CH3O minus. Okay, so which means that it's a good nucleophile. Okay, fairly a good nucleophile. So cis-1-bromo 2-methyl cyclohexane. Let's go ahead and write the structure for this one. So the relation is 1,2, so 1-bromo, 2-methyl, so 2-methyl, excuse me, right there. So CH3, or I can just leave it like that. And this is going to be a cis. So if it is cis, that means that I have wedges on both sides, okay, for this. And let me make this a little bit neat for you so you don't think I'm very untidy, because I can be. But in any case, so this is what we have to start with. So when we are looking at something like this and you're thinking, what am I doing here? Am I doing substitution? Am I doing elimination over here? So in this case, when you look at the halide that you have, okay, and the leaving group that you have, it is a nice secondary leaving group. You also have a little bit of steric hindrance going on because of the CH3 on this side, so which means that substitution may be not possible so much, okay, which means that we are looking at elimination. Okay, so that's one thing that we have to think about. So when we look at elimination, then now we have to think, is it going to be E1 or is it going to be E2? So with the secondary halide, it can be either E1 or E2, okay? And here is the big clue as to why we are going to say that this is going to be more like an E2 mechanism, and that's because the stereochemistry is given to us, okay? For E1, you would have like a tertiary halide or solvolysis or something like that, because in the E1, the nucleophile is not really important, okay? But in this case, the nucleophile is important because it's a strong nucleophile. Methoxide is fairly okay, all right? And it's a negatively charged nucleophile, so it's kind of an important one. Okay, so now we look at something like this, which is the substrate. So if I'm looking at an E2 mechanism, then I have to think, okay, why is the stereochemistry given to me? So the stereochemistry is given to you so that you can think about how elimination actually takes place. And not just elimination, it's actually E2, okay? And for E2 eliminations, you have to think about anti-periplanar elimination, okay? So anti-periplanar means that you have the leaving group, okay? So let me write that over here. You have the leaving group, and the hydrogen that's going to go away, these should be at 180 degrees to each other, okay? That's the important thing. So that's anti-periplanar. So let's go ahead and write the structure out for cyclohexane in the chair conformation, okay? Because when you have something like this given to you where you have a cis-1-bromo or cis or trans or something like that, you're better off going ahead and drawing out the chair conformation, because that's very clear how you're going to see your cis and trans. So cis actually means they're both going in the same direction. So same direction means that I'm going to go ahead and draw my bromine over here. Now remember, your leaving group always has to be axial, okay? Your leaving group cannot be equatorial, it has to be axial. So I always start with my axial on the top right corner. So here is the axial bromine. Now the methyl group is going in the same direction, which means it's also going up, which means that this is going to be the methyl group. So this is the cis relationship that we have. Okay, so now let's go ahead and identify all our anti-periplanar, or we can go ahead and identify all the hydrogens we have. Now, since we are going to do an E2 elimination, for an E2 elimination, we need to make sure that we have a 1,2 elimination. 1 being the carbon that has the leaving group, and then 2 being the carbon that's next to it, okay, from where the hydrogen is going to go out. So then let's go ahead and draw the hydrogens out. Hydrogen is going down over here, and then hydrogen here, since bromine is going up on the carbon number 1, so carbon number 2 is going down, and there's also a hydrogen going up. Okay, now let's talk about the anti-periplanar, okay, aspect of this. The anti-periplanar aspect of this is that you have the hydrogen here and the bromine here. They're going completely in opposite direction, so that's anti-periplanar. What else is anti-periplanar is this hydrogen. Okay, so now you have two hydrogens in which you have the anti-periplanar relationship. Okay, so I'm going to go ahead and draw this all out again so that it's kind of nice and clear. And I will draw both my hydrogens as well. So here is the bromine. Here is the methyl group, okay, and you can write the CH3 if you want to. And then we have two hydrogens anti-periplanar. One hydrogen is going to be here and one hydrogen is going to be here, okay. And so then now time for the mechanism. So because I have two anti-periplanar hydrogens, I can actually have two reactions going on, okay, or two eliminations going on. So I'm going to do two eliminations here, and remember my mechanism is E2, so OCH3 minus, that's the base, okay, that I'm going to have. And so in the first case, what I will have is that the methoxide will come and pick this hydrogen. The hydrogen is going to leave its electrons over here and bromine is going to go away. Okay, so that's the first case that happens. And so then this is going to be my product, and the bromine is gone. The hydrogen left its electrons over here and this methyl group is still here. Okay, so that's that. Now let's look at the next one. Okay, the second product, because now you have the OCH3 minus the methoxide here, and now this one comes for the other hydrogen that we have. This other hydrogen is going to leave its electrons down here and the bromine is still going to leave. Okay, so that's going to happen. And so then this is what we have. The bromine is gone, the methyl group is still there, and now what we have is of course a double bond right here. Okay, so those are the two products we have. Now this is drawn as chair conformation, but we can go ahead and draw this out so that we can see it more like what we are used to seeing. Okay, and so here is the CH3 and 1, 2, 3. So 1, 2, 3, that's where the double bond is. And in case of the other one now, this is what we have. That's the CH3 and the double bond is right on it. Okay, so these are the two products that are formed. Now, are both going to form? Yes. Okay, you will have both will form. Okay, because both are possible. So if you have both forming, now you have to decide, okay, which one is going to be the predominant product. So in this case, the predominant product is going to be the green one. Okay, why? Because that is the Zaitsev's product. And the Zaitsev's product, remember, is the one where the alkene is more stable. Okay, and the other one where the alkene is not very stable is called the Hoffman product. Okay, and so the Zaitsev's product is more stable, so Hoffman product is going to be the minor, and the Zaitsev's product is going to be the major product form. And usually if you have more than one product forming, you should try to write out which one is going to be the major and which is minor. So again, this question was essentially about anti-periplanar elimination, and anti-periplanar eliminations are usually going to be for E2 elimination, not for E1, because E1 are carbocation based.